we doing, guys? Question?
Yes.
I know you work out the one on the NICOL page with the NICOL and the AOH. And I heard you saying it was assumed to be aqueous, so was that NICOL first speak protein from water and become positive?
No, you only protonate something with strong acid, especially in this class. There's no acid present. Water's not an acid, it's definitely not a strong acid. There's nothing to protonate. You only protonate carbonyl or nitrile or alcohol with strong acid. Sulfuric acid, HCl. There's no acid present. So what's the first step? Hydroxide does nucleophilic addition to the carbon. Yeah. Adrian?
In the mechanism section, the workbook, there's a phenol that's acting epoxide. And a question about why it shows the carbon didn't.
What page?
42A.
Page 42. We have sodium hydroxide, we have an acidic phenol. The first step is going to be proton extraction, acid base. So the first step is to form that. Then what?
I was even understand why it wouldn't say we write carbon together.
What is your rationale?
The chlorine, the withdrawing, making it carbon more positive, and the two metals.
Okay, that's a good argument for why it should attack it. There's more partial plus here than there. Right? Okay.
And I mean, I see in the answer that it doesn't.
Well, you can also see right here that it doesn't, because the oxygen is
Right.
bonded to the carbon with the two methyls.
So my question
So you
is-
gave a rationale for why it should. Well, give me a rationale for why it should not.
Not where the answer is.
Right. That's my only
Okay?
rationale.
Well, that's good, because you are doing a mechanism. You see where you need to go.
Right.
Okay? So you need to go that way. What's another rationale, if you didn't see that, what's a rationale?
It's larger.
Yeah, these chlorines are larger, and what do these chlorines have around it? Lone pairs. Not only do they have the valence electron lone pairs, they also have subshell lone pairs. These chlorines are big with lone pairs around them. Now we usually don't, they're big. And they have electrons around them. And these are here, these electrons, when they come close, they're going to kind of repel. So that's maybe an argument of why it does not. A lot of times you have conflicting arguments. You have to decide which way you want to go based on observation, or maybe based on how you need to go because you got to attack over there.
Yeah.
Or maybe our putting partial plus here is not actually correct because maybe that partial plus is drawing these electrons this way. Maybe we really need to do some more extensive computational modeling on that. In the end, sometimes you have conflicting arguments in organic chemistry, and you have to be comfortable with that to be able to make an argument for both cases. Ultimately, you have to go to the lab and see which one wins out. If you go to the lab, we find that that product over the rarest form. Other questions? We've had 2 questions. I need 3 this morning. Yes.
Go ahead.
Oh, no, go ahead.
We can get 4. Jason?
Number 17 on page 49.
Multiple choice.
Is this just an acid-base reaction?
Well, this is a carboxylic acid. This is a CH3 minus, essentially. You think that's basic?
Yeah.
Yeah, that's a very strong base. And good nucleophile in the form of Grignard. What's going to happen? It's just going to take the H. What are we going to make? Which one?
The answer is D.
D. This takes an H, makes methane, and you get the O minus. Methane, O minus. That is O minus, right? That's a minus. That's an Mg. That's an Mg2 plus, and that's a minus. You can show it like a formula. That's just your O minus. Yeah, just an acid-base reaction. Anytime you have a strong base and acid, it's going to happen. You can't say, hold on, Grignard, I want you to ignore that little proton. All right? It won't listen to you. Questions?
Number 9 on page 48. I get why C is the answer. I don't get why A is not the answer. I picked A and C, but it's wrong. It's actually
What's the right answer?
just C.
C is the answer given. Which of the following converts benzoyl chloride to phenylpropyl ketone? Phenylpropyl ketone. That's kind of a slang way to name ketones. That's what that is in good deal. Which following converts benzoyl chloride into that? We need to replace the chlorine with a propyl. Which one's going to do it?
C, but I thought A was
C. This is what we ended with on Friday. Organocuprates. R2Cu lithium. Here R is propyl. Good way to make ketones. Why is it not A? Because A is a propyl in the form of a Grignard. Grignards do not stop. Grignard is going to react with this again. And you eventually, after you get proton on there, you're going to have 2 propyls there. You're going to get that tertiary alcohol. Grignards do not stop. You will not get a good yield of the ketone. Cuprates stop. Propyl lithium is just like Grignard. Neither one of these will stop. Neither one of them are viable, so it's neither D or E, it's C. Organocuprate, also known as a Gilman reagent. And again, that's where we ended last time. Let's pick up where we ended last time. By the way, we do have the information session tomorrow. If nothing else, you come and get some free pizza. 1 o'clock, Science Hall, 10:40. Anybody coming to this tomorrow? Everybody have a career plan in mind? Okay. Let's look at the info sheet. I don't have info sheet. The outline that we left off with. At the bottom, there's your cuprates. Adding to acid chloride, great way to make ketones. By the way, cuprates do not react with esters. They only react with acid chlorides. That's just a miscellaneous comment. We will see organocuprates during test 4. Again, Let's look at number 8. We'll also look back at the front page. The warm-up question. Okay, if you're reacting amide, primary, it can be secondary or tertiary, with LAH, what do you get? This is a source of H minus. H minus adds, electrons up. Let's see if we can work our way towards the product. Electrons up, nucleophilic addition. So H minus just did a nucleophilic addition, we get this. What you want to do next?
That's it. H plus source.
Trey?
They have an H plus source.
You just want to have an H plus source. And call that final product? Jason?
The O minus attacks the ALH3.
You've been doing some reading. Yeah? Anybody else been doing some reading? First off, we're not going to do this. We have a leaving group here. I thought what you might say is anytime you can reform pi bond, kick off a leaving group, we would do that. And we might get what? Aldehyde? Yeah? With acid derivatives, you never just give a proton source and this is it. You're never going to get two leaving groups on the product. Chemistry keeps going until it can't go any further. You could possibly reform carbonyl, kick off this, make aldehyde. Then H minus could add again, and you may end up with an alcohol. But that actually does not go this way. What happens instead, Jason?
It becomes a leaving group.
What do we have left here? We have ALH3 after this gives up an H minus. With amides, this does not happen. Nitrogen's not a great leaving group. It can leave. We've seen it leave. It has to leave when you hydrolyze an amide to a carboxylic acid under basic conditions. But here it turns out it does not leave. This is an interesting result. It's like, hold on, oxygen, you're not going to kick me off. Not going to happen. Not this time. Instead, these electrons coordinate with aluminum. Just like Friedel-Crafts acylation. Aluminum, a neutral aluminum, is a Lewis acid. That gives ALH3 minus and now that this oxygen is neutral, it can potentially leave. And now the nitrogen says, anytime I make a pi bond and kick off a leaving group, that's what we're going to do. And that gives phenyl this is actually 2 minus up here. there's a couple of steps that are usually not shown here. For example, this does not look good, 2 minuses. But see, when this aluminum becomes minus again, what does it start shooting off? Yeah, you see this now shoots off more H minuses. So this can become neutral by just supplying more H minuses. Now the final product of this reaction is the amine. When you react an anode with LAH, you essentially just get rid of the oxygen and replace it with what? 2 H's. We've already got 1 H on there. How do we get another? If we bring in another H minus, boom, and move these over, that looks like a protonated carbonyl. I mean, if I had a carbonyl with a proton on it, don't we add the carbonyls, electron on the oxygen? Add here, electron on it. And what does this movement give? That gives your final product. So what does LAH convert an amide to? Amine. What does it remove? Removes the oxygen, replaces it with 2 H's. It does not have to be benzylic. This can be anything. Questions about this mechanism? Sure.
Does the second H minus come from the AlH3 minus?
Yeah, this can essentially, that can supply 4 H minuses. I didn't go through the exact details. That aluminum shoots out an H minus, it wants to go neutral. Matt?
Does oil with NH2 or could those hydrogens be any artery?
Yes, they can be primary, secondary, or tertiary amides. Any type of amide. Karen?
When the electrons come down on the metal, how do they like come to the nitrogen and not the
At what point?
right there?
Right here?
No. There.
You want to make pi bond here
No.
and kick off what? I didn't show the product, but we know this is the product that's formed. So you don't want to kick off the nitrogen. If you did, you wouldn't have the carbon bond to the nitrogen. Knowing this is the product form, I could have showed you this first. What leaves the carbon? The oxygen leaves. You see right here, you might think, bring this down, kick off nitrogen. Nitrogen is not the best leaving group. It can leave here. And the first chemist to ever run this reaction was thinking the nitrogen was going to leave. Back in 1893. Dr. John Anderson did this, and he wrote in his notebook, I think the nitrogen will leave. But when he did, and he even drew a mechanism. He said he was going to get this, but when he analyzed his product, he ended up with that. So then he had to say, well, what the heck's going on here? And he said that at this point, the nitrogen just didn't want to leave, apparently, and he proposed that instead the oxygen left. But do we really want to move these in and kick off at O2 minus? We don't want to do that. So somehow we got to make this neutral before we kick it off. There's no protons, so how would you propose making this neutral? See, he was friends with Friedels and Crafts, and they knew that things coordinate with aluminum. So he was talking with them one evening, and so he came up with this idea: make it neutral, and then you can kick it off, and it's only O minus. And then you can maybe add this here, and So he proposed this mechanism to make the product that he indeed made. And since then, nobody's had come up with a better mechanism. I made 3/4 of that up. Any questions? Okay. Let's move to nitriles. What if we react to nitrile with LEH? Well, in general, what type of reagent is LEH? Is it an oxidizer? Reducing agent. Supplies H minus. That's a reduction. When you add H's, that's a reduction. We're reducing the nitrile, LEH. What kind of reagent is dibol H? Reducer. What kind of reagent is H2? H2 adds H's. Yeah, see, all this is reduction. Now, up here, we're going to do a complete reduction. Here, we're going to do partial. Dibol does partial. Remember I did partial before? We're going to do partial here again. But before we do LEH, let's show the product that H2 would give, like with a nickel catalyst or something. Well, we have RC triple bond N with a lone pair. What if we had RC triple bond C with another R? What would happen if we reacted this with H2 in there? With two equivalents. Basically, well, you don't really need to say that because we know what's going to happen with, what do we get? CH2, CH2. Full reduction. What's the intermediate here that's not stopped yet? Is it cis or trans? It's the cis alkene. But it doesn't stop there, it goes all the way. So the same thing up here. We have triple bond. It's the same chemistry. First thing is we add two H's. Get the alkene. When we add two H's up here, that's triple bond, right? We're going to get that. H added to each one, becomes double bond, but it doesn't stop there. If we add again, what do we get? Instead of C triple bond N, we now have CH2 NH2. Instead of C triple bond C, we have CH2 CH2. So this is like with nickel or palladium, etc. So it's the same as your alkyne. Partial reduction, full reduction. What is the full reduction? What functional group did we make? Primary amine. It has to be a primary amine. You cannot have an R group on the nitrogen here, so you cannot have one there. All you can do is two H's, two H's. It's primary amine. Full reduction of nitriles gives primary amine. What is the intermediate called? What's the name of this functional group? It's a carbon double bond N. You've all made one in lab. Imine. Imine. Imine is analogous to carbonyl. If under my hand was oxygen, what would that be over there? It'd be a carbonyl. I mean, it'd be an aldehyde, a precise type of carbonyl. You replace the oxygen of a carbonyl with a nitrogen, it's an imine. And of course, the nitrogen can have one more thing on it, because it's trivalent. Imine. Now, LAH will also do this. Reduction of a nitrile with LAH also gives the primary amine. Now, with hydrogen, it's sort of, like this. It sits on the catalyst and boom, the H's are shot in cis. And then boom, the H's are shot in and you get product. With hydride, we can show more of a mechanism. Let's see. H minus. A dipole here. Electrons move over. We get R, C, H, N. And that's a minus charge now. What do you want to do next? Novel idea. Why do you want to do that? Or yeah. Some books may show, or somebody may say, well, hey, what else can you do? We're trying to get two H's here, and we ultimately need two H's here. All we have is hydride. Is hydride going to add an H here? No. N minus doesn't react with H minus to NH. You're going to have two extra electrons. You need H plus. There's no H plus here. Not until we work it up. We could show another H minus adding here and these moving here, but that would make that 2 minus. Never make 2 minus in organic chemistry. So how can we take this back to neutral? We do have the ALH3, which this can coordinate with. We can get to this point. That's back to neutral now. Now at this point, this can shoot off an H minus, and that can become neutral. But I'm not going to deal with that. But H minus can be shot off, and now H minus can come in here again and do it again. And now we have two H's on that carbon. I'm going to call that ALH2 now. Let's pretend that H minus came from here. That went back to neutral when it shot off an H minus. So now that's minus again. Came in a second lone pair. We get to this. And this is in step 1. You throw in water and you get the final product. So this would require H2O workup. That's where the protons come from. We can envision the first one coming from just the minus taking an H. This bond gets hydrolyzed off. The oxygen attacks the aluminum. This is the leaving group, and then the leaving group picks up another H. We really won't look at this too much. Basically, when you reduce the nitrile with hydride, we can do a ionic mechanism. H minus adding again, and then that's picking up protons from water. In the end, both of these methods give primary amine. What do you get when you react this with dibol H? You Anybody, what do we know about Dibol H?
Doesn't know a lot.
Hindered hydride source. It's going to stop intermediate. What is the intermediate here? Imine. Partial reduction of the nitrile with Dibol H gives the imine. And then we can do something with that. During test 4, we will do chemistry with that. For now, we're just going to stop at the imine. Adrian.
Is it the same where it bonds with the aluminum and then you add water? Or no?
What do you ask?
Just. So if it's just uneven on the product, it's not.
Well, the first step is H minus, adding to the,
Right.
adding to here.
But then it is negative.
I think, better question might be where's the H come from?
Right, that's.
You're going to have an H plus workup or H2O workup to get the imine. You do hydride addition to get this, and then you add in water, and it gives you your imine. I mean, you can show this associated with the aluminum for the Dibol, but it doesn't add again. So a partial reduction of a nitrile gives what? Imine. Question?
Does NaBH4 not work?
Good question. Sodium borohydride typically only reacts with aldehydes and ketones. It can reduce imine, which you do in lab. But there's several reactions that LAH will do, but sodium borohydride will not. LAH is a stronger reducing agent. Sodium borohydride will do some of these reactions if you include a catalyst. But we're getting kind of into the weeds there, and typically, in general, sodium borohydride only aldehydes and ketones, or imines, which is a derivative of an aldehyde. LAH will react with acid derivatives, esters, nitriles. Okay. Put these down here. How do we do on these? So we have total magnesium bromide. That's the Grignard. Grignard adds here, electrons up. We end up with that product there. How we do? Next one, we have H minus. That's here, electrons up. We get that product right there. How we do? Question?
With the first one, the radio, if you did not supply a hydrogen source, would it continue to react and move the oxygen fluid?
No, after you had the Grignard, you get that. right?
Would it be able to react with the magnesium, with the option to react with magnesium brine? And go neutral again? And then another mineral,
Well, hold on. First off, that's a minus. Anywhere you got a minus, there should be a counter plus.
using the magnesium bromide plus.
I mean, you show the magnesium Br right there, magnesium plus. I mean, that's how that exists. Anytime I draw a minus on the board, there's got to be a plus with it. I don't always draw the plus. The plus is there. But what do you want to do after that, though?
Well, if you have two equivalents of the Grignard reagent, with another filter, we have to have to
But you don't have a carbonyl. How are you going to reform carbonyl? Or pi bond. If we have nitrogen over here, maybe you can kick that off. But we don't have any long pairs here. Nothing has a long pair. Nothing's going to make pi bond and kick that off. With aldehydes and ketones, one nucleophilic addition, and then game over. Down here, H minus added, electrons up, that became minus, game over. All you can do is put proton on. Okay? There's some appropriate work up here. It's going to become H. At the top of the very beginning, underline. Assume aqueous workup for all reactions. We do aqueous workup, these O minuses are going to pick up proton and become OH. Okay? Acid chloride, Grignard. What's the product? Somebody got it?
There's your two ethyls off of it.
This tertiary alcohol. How we do? Questions about that one? Okay, next one. I'm assuming you have done all these, right? Same reagent. Here we have a cuprate product. Ketone. Do I see what's going on? Ethyl anion attacks carbonyl, electrons up, back down, kick off chlorine. Give this. Does it add again? Cuprate stop at ketones. Great way to make ketone. Grignard adds again. Add again, you end up with two alkyls, O minus picks up proton, you get the previous product. How about on the very front? What reagent will react with A to give tramadol? Pain medication.
Grignard, ethyl, fatal.
You've got a ketone here you were given to start with. Which bond do we need to make? It looks like we can add that nucleophile to the carbonyl, electrons up, and then the carbonyl picks up an H, or the oxygen picks up an H in some type of workup. How do you supply that nucleophile? Grignard. You need this Grignard, and that carbanion, right? This is essentially a carbanion. 2 plus, Br minus. This carbanion attacks carbonyl, electrons up. You make that bond, and then this picks up proton with aqueous workup. We'll learn how to make such a compound during test 4. Bond right here. You can write this down. This would come from a Michael reaction. A Michael adduct or product. We'll learn about Michael reactions during test 4. So does everybody see how this could have added to this carbonyl? Nucleophile. When we were doing epoxides, we said nucleophile carbon, carbon OH. It's kind of like nucleophile carbon OH. One carbon. Well, anytime you see carbonyl, you can bring in a nucleophile unless you have nucleophile carbon OH. Yeah. Okay. I assume you can show a fluid structure from tramadol hydrochloride. On the very back, we'll end with this maybe. Synthesis of Allegra. What's the very last step in this synthesis of Allegra? Reaction of 27 with what? Sodium borohydride? What's the conversion that's taking place? The ketone is being reduced to the alcohol, H minus. And then this picks up an H from proton. Why do they include sodium hydroxide in the reaction? You've got this acidic proton right here. They include sodium hydroxide to take the H. Perhaps so the H minus won't take the H. Now they show this in the acidic form. What are they leaving out here? How's this going to exist under basic conditions? It should be minus. So how do they get the H on there? They can beat water. Water's not strong enough to put a proton on here. This requires addition of acid at the end. They conveniently leave that out. Very often workup steps are kind of omitted because people just don't want to convolute things. It's just assumed. Okay? When I get the proton on there, The second step is probably add HCl. It's like you're going to get proton on there. Lots of reactions on here. Friedel-Crafts, SN2. And going from 25 to 26 is just an ester hydrolysis. Got this ester out here, they hydrolyze it, liberate the alcohol. Okay. Squiggly line is a way to show that it's racemic. It is chiral. I have always just sort of shown OH and then said racemic. But a squiggly line is a way to show that it's racemic. Because if that was just a bond like that and nothing was said, people would say, well, is it RS? Or why didn't they even consider stereochemistry? But the fact that they showed it squiggly means they are telling you something. They're like, hey, I know this chiral, but it's RNS, and so it's a generic way to show that. Or they could have showed two different molecules. They could have showed one where it was bold, and they could have showed one where it was dashed. But apparently Allegra there's only one chiral carbon and it's right there. Nothing else is chiral. That's not chiral, that's not chiral. Apparently Allegra is a racemic mixture. I don't know. I mean, ibuprofen's a racemic mixture, but only one of them works. Whenever you take ibuprofen, half the molecule doesn't work. Half the drug doesn't work. It's really a lie. The body converts one enantiomer to the other, so actually it all works, but not in the beginning form. Okay, we need to move on. Test on Wednesday. Acid derivatives, we did some nomenclature of acids and esters and a little bit of amides. Everything else we've covered, outlined, all the way through what we finished here with this last sheet. Some aldehyde ketone reactions in there. Any questions about IR?
Are we going to have a multi-step similar to last time?
Having what?
A multi-step synthesis similar to last time?
Multi-step synthesis. We really didn't do much of that. So no. There may be some sort of intermediate multi-step synthesis, like a line reaction that has 2 or 3 steps. But I don't foresee some like here's a product, give a multi-step synthesis starting with benzene or something. Question? Adrian?
Oh, it could be if there was the molecule and say there's 3 ways we can make it.
Uh-huh. Was there any questions about IR? Any questions about IR? Mark?
On the last example, the IR said,
The nitrile?
yeah. So how do we know it's C11O and C.
I didn't quite hear you. How do you know it's C double bond O and not a CN?
Yeah, I mean, C11C and not C11O.
Well, there's no carbonyl. I mean, the CN is right here, yeah? About 2200? So I'm not sure what your question was. Are you asking why that's not a CO?
Yeah.
Well, the first answer, which I don't think I even stated, there's no CO in the molecule. But why is that not a CO? Because it's too weak to be a CO. Carbonyl is usually one of the strongest peaks in your IR. Okay? Also, what's the position of this? What's the position of that peak? It should be low 1600s. I don't really see it here. Is that a 6? This doesn't look quite right. I mean, it looks to me like it's about below 1650. Is that right?
Yeah, I think it's
1599 would be right there. Well, it looks too low to be a carbonyl and too weak to be a carbonyl. Here's a cyano group. Questions about IR? You okay in the workbook?
It's a little confusing, but we asked all our questions today. Some of we had covered it.
Guys, I'd recommend you get started on your report for lab.